question here is, what does HO have to be in terms of R, the radius of this loop here, without friction, such that the box here can slide all the way down and negotiate the loop here? Okay, so two areas of concern are going to be here and here. Okay, all right. So, any suggestions how we should start, or what should be zero? Okay, when we look at this problem here, what should be zero? Okay, initial kinetic energy is going to be zero. So is friction. Good. So those two now, I'm going to post it on YouTube, give you a link to my YouTube channel, so you don't have to just kind of watch. You don't need to write this down. Because I think after writing down, you kind of forget what's going on. All right, so let's go ahead and put in values that we know of. Okay, what's my starting potential energy gravitational? HO. Yeah, you're going to be precise. So it's going to be mgHO. That's my starting potential energy. In fact, this is the energy that I had to start with for the entire problem. Now, it's going to slide down here. It's going to end up right here. Okay? So I want to examine right here. Will it have potential energy here? Will it have kinetic energy? Yes. So here, I'm going to have kinetic energy, which will have 1/2 mv squared plus mg. Now, how do I express the height here? 2r. This is r, that's r, so 2r would be the height. So that's the first critical substitution that I need to be aware of. It is 2r. Okay. Now, take a step back. What cancels out? Well, we'll do mass right now. Mass for right now. Now, on the first question, I asked, what's the role of mass on the free response? Everybody missed that question. Maybe 2 people got it right. Mass cancels out. Or on the ramp, mass makes no difference. But when you encounter friction, mass does make a difference. So a lot of people did not articulate that very closely. Okay. So we're here. All right. So let's kind of clean this up a little bit. Let's solve this for HO. I'm going to divide by G everywhere. So this becomes what? V squared over 2G, right? Plus this will be, what's it? Just 2R? Mm-hmm. Okay, so we're almost there. Okay, now if I stopped here, did I solve for HO in terms of R? No, there's a G here and there's a V there. I'm not done. If you stopped here, you would get it wrong. Okay, we need to go a little bit further. Now, so I now need to look at the speed or the velocity here. Let's examine this in more detail. Okay. So take a look at it. So here's the top of the loop here, right? Here's our box here. Okay. Let's do all the forces acting on that. What forces are acting on that? Okay. Normal force is acting in this direction. Okay. What else is acting? Gravity. Gravity, or we call it mg, is also acting in that direction. So we have 2 forces, normal force and gravity, acting in this direction. Which way is the acceleration vector acting? Down. Yes, toward the center, yes. The acceleration vector is also acting in that direction as well. So a good hint, whichever direction this is pointing, make that positive. So in this case, these are both positive. So everything going down will give a positive value to it. So now, from here, we will go sum of the forces, right, is equal to m, and we'll call this AC, which is centripetal acceleration. Right? Now, remember the elevator problem way back about a couple months ago? This is the elevator problem. Okay. So what are the 2 forces going down? Normal force plus mg is equal to m. Now, I'm going to substitute the value or the equation for centripetal acceleration, which should be v squared over r. Okay, so we have this. Okay. All right, now, okay, when I'm here, okay, take a look at it here. Okay, what is critical? Now, if I go too slow, what happens to the normal force? If the normal force is 0, what happens to the block? It falls. So when normal force is 0 is what's critical. So normal force is 0. That's when this could possibly fall. So we'll have here mg is equal to mv squared over r. Okay? If that's 0, the block falls. Block falls. All right? So looking at that, can I solve for v? That would be yes. Actually V squared should equal, G times R? That's V squared. Okay. Now, we're almost done. I look at this, and I look at that. Can I make the substitution? Yes. Okay, just I'm being videotaped. I have to go fast, okay, because I want to make this into a 10-minute video. So HO is here, so this goes into here, so this will be GR over 2G plus 2R, like so. And look at that, that cancels out. So we have HO is equal to 1/2 R plus 2R. And if I do my math correctly, this should be 5/2 R. 5/2 R, or 2.5 times the radius. So when you go on a roller coaster, which I'm going to be going to Great America on Saturday, I'll try to take a video of the roller coaster ride. If you're on a loop here, for gravitational energy only, you have to go without friction 2.5 times the radius you have to start from. So any loop you look at, you know you have to go 2.5 times greater than that in order to go all the way around the loop. Okay. All right, so now we solved our problem here. So HO is now in terms of R. And then we are done.